Hello students, in the previous lecture I started the topic design factors of biomedical instrumentation system. I told you while designing any biomedical instrumentation system or man instrument system, there are certain factors that need to be considered for the designing purpose, or you can say these are the specification factors. Means for a particular application, if you have to choose a biomedical instrument, then what you will do, you will go for the specifications of the different instruments available, and then you will find that instrument whose specifications will match your requirement. So that's why we need to study all the specification factors in detail. So I already discussed range, the specification factors or design factors like range, sensitivity, linearity, hysteresis. These I have discussed. Now I'll start with frequency response. So what is frequency response of a biomedical instrument? You can say it is the variation of sensitivity with respect to the frequency range of the measurement. In the x-axis we have the frequency, and in the y-axis we have the gain, or you can say the sensitivity. So it is the variation in sensitivity with respect to the frequency range of the instrument. Now for the instrument to faithfully reproduce the original physiological signal, what are the requirements? There are two requirements. First, for the entire frequency range, the sensitivity should be constant. Again I am repeating, for faithful reproduction of the original physiological signal. That original physiological signal might be consisting of varieties of frequencies, might be consisting of number of frequencies. So for original reproduction of that physiological signal, the instrument should have equal sensitivity for the entire frequency range. And second point, it should be able to respond rapidly to reproduce all the frequency components. Only then you will get the faithful reproduction of the original signal through that biomedical instrumentation system or the instrument. So this condition, you can say it is called as the flat frequency response. You can say this is the flat frequency response. So what is flat frequency response? Where it is that response where for all the frequency range of the instrument the sensitivity is constant. So this was about flat frequency response, and it is a requirement for an instrument that the instrument should have flat frequency response to faithfully reproduce the original signal. Now next that I'll be discussing is the next design factor that I'll be discussing is the accuracy. So what is accuracy? Basically accuracy, as you all know, that it is measured in terms of error. What is error? Error is the difference between the true value and the measured value, and accuracy is measured in terms of error. If the error produced by an instrument is more, we say that the instrument is less accurate, or if the error produced by an instrument is less, we say that the instrument is more accurate. So accuracy is measured in terms of error. So what are the types of error that can be introduced, that can be present in the measurement of a biomedical instrumentation system or biomedical instrument, which may alter the accuracy? So what are the errors that might present? So there are many types of error, like parallax errors might be present. Suppose the biomedical instrument system has measured some physiological signal and has given the output. Now human beings are not able to read that data accurately because of the meter, because of the pointer system of the display of that man instrument system. Suppose the man instrument system in its display unit has the pointer. So because of that pointer, the parallax error is getting introduced, or the error might occur in the instrumentation system or in the biomedical instrumentation system might be due to the change in atmospheric pressure, or you can say the change in atmospheric conditions. And because of the change in atmospheric conditions, there are various factors that might get affected, like the resistance might get changed, etc. And because of that, the errors may get introduced. Error may be also due to the drift or temperature variations. Then it may also occur if you have not properly done the instrument zeroing before using that instrument, then the error may get introduced. What is instrument zeroing? That is when no input is given to the instrument should show zero output. So that is called instrument zeroing. So it should be done, instrument zeroing should be done before using the instrument. Then error might be due to the loading effect also. That what is loading effect? Suppose the instrument, biomedical instrument that you are using for measuring a physiological variable from a subject, then the introduction of that biomedical instrument to the subject for the measurement may extract energy from the subject, and because of that the original physiological signal may get altered. So because of the loading effect also error may occur. So for an instrument, what is the necessity? The accuracy should be high, or you can say the error should be low. Now next point under this design factor is signal to noise ratio. So what is signal to noise ratio? Basically in a hospital environment, various types of noises might be present. It might be due to power line frequency noise, or noise might be due to the interference due to electromagnetic or electrostatic equipments. So these types of noise may get usually picked up by the long leads of the instrument, or the long leads that are connecting two or more instruments. These type of noises might get picked up by these long leads. So what is the requirement? The requirement is signal to noise ratio should be as high as possible. So basically what is signal to noise ratio? It is the ratio between the output magnitude of the instrument and the noise level. So what is the requirement for an ideal instrument? The signal to noise ratio should be as high as possible. Next factor that I am going to discuss is stability. So basically what happens, suppose there is an instrument, biomedical instrument, you are giving some input and it is producing the output. Now suddenly the input is changed, you have changed the input, or the input gets changed. Because of that, what will happen? Suppose this is the input gets, initially the input was this, now the input gets changed to this, and because of that the output will go under vibrations. There will be oscillations in the output. You will get to see the oscillations in the output, and then after a certain point of time you will get to see that it will resume back to the steady state. So what is stability? It is the ability of the instrument or the system to resume to steady state condition. This is the steady state condition for this input. So to resume to the steady state condition rather than following a disturbance. So an ideal instrument should be highly stable, and it should be highly stable over the useful range, over the entire frequency range, or over the, you can say, over the entire measurement range of that instrument. It should be highly stable, that if the input is changed at an instant, then the output of that instrument should quickly resume to the steady state position. Next design factor that I am going to discuss is isolation. So what happens actually here in biomedical instrumentation system, we are introducing the instrument to measure a physiological variable from a subject, and here the subject is a living being. You can see here the subject is a human being, or here the subject is an experimental animal. So here the subject is a living being. So for this case, the biomedical instrument should not produce any direct electrical connection between the subject and the ground. You getting my point? The biomedical instrument, it should not produce, because the biomedical instrument is introduced to the subject for measurement, so it should not produce any direct electrical connection between the subject and the ground. Here the subject is the living being. So for electrical safety, for maintaining the electrical safety, or you can say to avoid interference between different instruments, electrical isolation is required. And how you can achieve the electrical isolation? Electrical isolation can be achieved by using magnetic or optical coupling techniques, or you can say by using wireless radio telemetry. So this was for an ideal instrument, it should be isolated. It should have proper electrical isolation to avoid health hazards. Next design factor, that is the last one I am going to discuss, is simplicity. So all the instruments, all the biomedical instruments should be as simple as possible, meaning any biomedical engineer should have this thing in his or her mind, that the biomedical instrumentation system that the person is going to design, that the engineer is going to design, should be as simple as possible, so that the chances of component or human error can be eliminated. So simplicity is very much required. Moreover, these type of biomedical instrumentation systems or biomedical instruments require calibrations before they are used. Every component of that instrumentation system should be individually calibrated, and once all the components are individually calibrated, and when they are assembled for this biomedical instrumentation, for making this biomedical instrumentation system, then the whole system should be calibrated as a whole. This whole system should be calibrated again. So calibration is very much required before performing measurements using this instrumentation system. So these were the design factors for a biomedical instrumentation system. So I am ending this class here. Thank you.